Balance and equilibrium, they're ideas that seem peaceful and harmonious. Surely that's what we want in life. Well, as an engineer, sometimes you need to upset the balance in the name of solving problems. Last time we discussed mass transfer and how two substances can form a mixture through processes like diffusion, where the individual molecules are driven by their concentration differences towards a state of chemical equilibrium. That means having the same concentration on either side of a boundary, or uniformly throughout a single container, like food dye mixed into a beaker of water. But what if one of the components of the mixture is more useful than the other? Worse still, what if one of the components is actively harmful and you need to isolate it? It's time to separate the wheat from the chaff. Much like we've seen for momentum and heat, different types of molecules, especially in liquids, are driven towards equilibrium by differences in their concentrations. For some liquids, this happens naturally through the process of diffusion, when the particles of a substance spread from a region of higher concentration to a region of lower concentration. But let's consider something a little different. Imagine thoroughly stirring some caramel sauce into butterscotch pudding. No complaints here. But accidentally mixing a dollop of mustard into your pudding, well, that's not going to taste so great. You're probably going to want to get it out of there, unless you have some very unusual tastes. Not that we're judging. Okay, so separating mustard from pudding might not sound too vital, but separating different types of chemicals from one another is something engineers need to do pretty often. More specifically, we often want to be able to purify chemicals or extract one particular product from an evenly balanced mixture. That can be a crucial step in tackling an engineering problem. To achieve this, engineers make clever use of temperature, pressure, and flow to create the right conditions for separating two or more substances. Concentration differences might cause substances to mix, but with the right apparatus, you can use mass transfer to isolate substances instead. Let's take a closer look at three particularly useful separation techniques: distillation, liquid-liquid extraction, and reverse osmosis. Now, if you've ever been to a bar, you'll know that the most popular drinks on the menu have one thing in common: ethanol. That's the type of alcohol people drink. And along with causing tipsy Saturday nights and terrible headaches on Sunday mornings, ethanol has lots of important industrial uses as a disinfectant, a preservative, and even a source of renewable fuel. But in the form we produce it, it's often mixed in with too much water for those purposes. Whatever you're using it for, you'll need to find a way to separate it into a purer state. And that's where a process like distillation can help. You might have heard of distillation before, and for good reason. It's really important for engineering. It's based on the fact that often the components in a mixture have different boiling points and volatilities. That is, their tendency to vaporize at a given temperature and pressure. A distillation column uses temperature to separate the chemicals in a mixture based on their different boiling points. You start by introducing the mixture into the column, which can contain several round platforms called plates that divide the column at different heights up its length. Each of the plates has little holes in it, like a sieve, and those columns, by the way, can be as tall as 2 stories high. One of the important features of a distillation column is that it's heated from the bottom so that the top is much cooler, setting up a gradient of warmer to cooler temperatures from bottom to top. That's going to be important for separating the substances. There are 2 things going on throughout the column. Liquid is falling down the column through the holes in the plates, or into the spillover, the gap between the plates and the walls of the column. Meanwhile, gas is rising up throughout the column, passing through the liquid and those same holes in the plates. Depending on the temperature at a given plate, the parts of the mixture that are still firmly in the liquid phase will tend to be drawn downwards, while those chemicals that are at the right temperature to become a gas will be drawn upwards by the rising vapor. So the more volatile substances transfer into the gas phase and join the rising vapor, while the less volatile substances, which are below their boiling points, channel downwards as a liquid. There's also some energy transfer going on. If some of the gas has risen high enough to cool off and become a liquid again, it releases some energy as it condenses. When that energy is absorbed by the more volatile substances in the liquid, it causes them to undergo a phase change, turning into a gas and travelling upwards. So you want the liquid and gas to interact as much as they can at every point in the column. The plates are positioned at certain heights up the column, so they're at the specific temperatures that work for the chemicals you want to separate. Over time, they'll collect concentrations of different chemicals in the mixture. And there you have it. Chemical separation. Like all processes in engineering, distillation isn't 100% efficient at yielding products. The concentration of the product might be higher than it was when it started, but it might not be high enough after just one pass through the column. Well, no problem. You can simply do what's known as reflux, where you pass the liquid back down to the bottom. There it enters the reboiler and rises as a gas to be further separated in the column. You can keep doing this until you've separated the mixture into all its components at the purities you want. Besides separating ethanol and water, this sort of process is also used to separate crude oil into different useful components like motor fuel and lubricants. For other types of mixtures, you might need a different strategy. Consider alcohol again, but this time mixed with oil. Introducing alcohol to vegetable oil, the kind you cook with, is part of the process of extracting lecithin, a mixture of fats. You can use it for all kinds of things, from making chocolate flow better to intensifying the colours in paint. As an added bonus, extracting lecithin also helps refine vegetable oil, but you generally don't want that alcohol still in the oil when you actually come to use it. That's where liquid-liquid extraction comes in. Liquid-liquid extraction is exactly what it sounds like, extracting something from one liquid into another. It's nice when engineers give these things sensible names. This time, instead of separating by temperature, you're separating liquids by density. Distillation works for chemicals that are willing to mix, like ethanol vapor and liquid water, so they can exchange volatile particles. For liquids that don't mix so easily, liquid-liquid extraction provides an alternative. In an extraction unit, the idea is to decontaminate the mixture by transferring the contaminant, in this case alcohol, to another liquid with a different density. The liquid you're transferring the contaminant into is called the solvent. With the alcohol oil example, the solvent would be water. The important thing is that the solvent can mix with the contaminant, but it won't mix with the product, the purified liquid that you want at the end. That way they can pass through one another while only exchanging the contaminant in the mixture. So to do the extraction, you put the denser of the two inputs, so either the mixture or the solvent, at the top and the lighter of the two inputs at the bottom. That way, when they enter the extraction unit, they'll swap places. The denser liquid sinks and the other floats up, forcing the solvent and the mixture through one another. In this case, water is denser than the oil-alcohol mixture, so you'd feed the solvent in at the top and the mixture at the bottom, but different scenarios might require that the solvent and the mixture be the other way around. Either way, you want to pick a solvent that the contaminant is more chemically attracted to than in the original mixture. In other words, that the contaminant is more soluble in. That way the contaminant will transfer to the solvent and get carried away with it, leaving behind a purer version of the product. Since alcohol mixes more easily with water than oil, it gets drawn into the water as the water passes through the mixture, leaving a purer form of oil. So even when temperature differences can't help you, solubility can. Other times, the best way to separate things is through reverse osmosis. That might sound like a science fiction surgical procedure, but it's really just a fancy term for filtering molecules or small particles from the medium they're mixed into. For example, of all the water on the Earth, only 2.5% of it is fresh water, the kind we drink, and most of that is locked up in glaciers. The rest of it is undrinkable salt water, the kind you find in the ocean, and the amount of fresh water available per person on Earth is rapidly shrinking. But if you can find a way to separate out the salt, you can make more fresh water from salt water. In other words, you need a way to tip the seesaw of chemical balance to isolate water from the stuff it's mixed with. To understand reverse osmosis, let's take a look at plain old osmosis first. Osmosis is based on the ideas of mass transfer we looked at in the last episode. You have two liquids on either side of a semi-permeable barrier, which allows the solvent to pass through, but not the other molecules in the mixture. In regular osmosis, the solvent moves from the side of the barrier with a higher concentration to the side with a lower concentration until both sides are in equilibrium. If we can reverse the process by forcing only the solvent through the barrier while leaving the other types of molecules behind, we can separate the two out. To make things less abstract, let's go back to our salt water conundrum. We want to filter out the salt from the salt water. We can do that with reverse osmosis. All you have to do is pressurize the water and force it through a semi-permeable barrier. With the right kind of filtering material, the water is forced through, while ions like salt and bigger things like other molecules, tiny bits of dirt and bacteria are held back and removed. The stuff that gets filtered out is known as a reject stream. At its best, reverse osmosis can remove over 99% of the salt and other unwanted stuff from the water. Some countries that don't have much fresh water, like Saudi Arabia, have giant plants that use reverse osmosis to generate over 1 million litres of fresh water every day. For the record, there are lots of other methods for separating the different mass species in a mixture, like absorption columns, stripping columns, dryers, humidifiers, evaporators, and more. Diffusion, liquid-liquid extraction, and reverse osmosis are 3 methods that come up a lot, but lots of the products we use every day are made of materials derived from some of the other processes. Unfortunately, rescuing your butterscotch pudding is more difficult than it seems. You'd have to use a combination of different techniques to separate components of the mustard and pudding, like distillation and filtration. And even then, in the process, you'd probably also separate the pudding itself into streams of isolated fats, sugars, dairy, starch, and salt. On second thought, maybe you should just have an apple instead. Today, we've covered the need for separating chemicals from one another and 3 different processes engineers use to achieve that separation. Distillation, which separates substances based on their different boiling points, liquid-liquid extraction, which uses differences in solubility to transfer a contaminant into a solvent, and reverse osmosis, which filters molecules from a solvent by pressurizing it through a semi-permeable barrier. Next time, we'll be taking a broader look at materials, what kinds there are, the properties they have, and how we use them to build everything from screwdrivers to skyscrapers. Crash Course Engineering is produced in association with PBS Digital Studios. For more inventive approaches to daily life, check out our sister channel, Reinventors, and meet scientists, inventors, and tinkerers who are working to create a more sustainable future. Crash Course is a Complexity production, and this episode was filmed in the Dr. Cheryl C. Kinney studio with the help of these wonderful people, and our amazing graphics team is Thought Cafe.